Okay, some sample problems for chapter 22. For this problem we have a bunch of charges and we're asked to calculate flux for some various surfaces, where flux is going to be the charge enclosed divided by epsilon naught, permeability of free space, which has a value of 8.85 times 10 to the negative 12th. It's going to have units of coulombs squared per Newton meters squared. So that's a capital N. There we go. So let's take a look at A, surface 1. Surface 1 is this guy right here. It has Q1 enclosed, so Q enclosed is just Q1. So therefore the flux is just going to be Q1, which is going to be 4 times 10 to the negative 9th coulombs, divided by the permeability of free space, 8.85 times 10 to the negative 12th, and I'm going to get my flux to be equal to 452 newtons meters squared per coulomb. For part number B, we're looking for surface 2. Surface 2 has Q2 enclosed, so Q enclosed is just Q2. Therefore the flux is going to be equal to negative 7.8 times 10 to the negative 9th coulombs, divided by the permeability of free space. I'm not going to bother writing it for you. The flux is going to be negative 881 Newton meters squared per coulomb. Negative flux means that flux is inward, which is what we'd expect. That is a negative charge. For C, we're looking at surface number 3. Surface number 3 has both Q1 and Q2 enclosed, so the flux is going to be the Q enclosed, the net Q, which is going to be equal to 4 times 10 to the negative 9th coulombs minus 7.8 times 10 to the negative 9th coulombs. Divide those guys by the permeability of free space, and we're going to get the flux to be negative 429 newtons meters squared per coulomb in part C. Part D, we're looking at surface number 4. Surface number 4 is, erase these guys to see it a little better. Surface number 4 is this purple guy right here, and it has Q1 and Q3 enclosed. So the flux is going to be Q1, 4 times 10 to the negative 9th, plus Q3, which is going to be 2.4 times 10 to the negative 9th coulombs, divided by epsilon naught. And we're going to get 723 newtons meters squared per coulomb. Lastly, E, surface number 5, the charge is going to be the net charge enclosed, which is going to be the sum of all three charges, so it's going to be 4 minus 7.8 plus 2.4, all of those guys multiplied by 10 to the negative 9th. Divide that by the permeability of free space, and we're going to get the net flux for surface number 5 to be negative 158 newtons meters squared per coulomb. For part F, it asks us, does the distribution matter? Long answer short, no, it doesn't matter. It doesn't matter how it's distributed. The only thing that matters for a flux is the net charge enclosed. Okay, problem number 17. Here we have a sphere. We know it's a spherical conductor, and we're given its diameter is 0.32 meters, and so that tells us that the radius is going to be half that. And really it's asking us for how many electrons do we have to put on the surface in order to get a field of 1150 towards the surface of the sphere. So first let's solve for how much charge we need to get. Hope you know by now that the electric field is going to be 1 over 4 pi epsilon naught, the charge divided by the radius of the sphere squared. We're using the radius of the sphere because we're really asked for it just outside of the sphere, so we can say that's close enough to the radius. Could also write this as k cubed divided by r squared, where k is the value we used a lot in the last chapter. So first let's go ahead and solve this guy for how much charge we need. That's going to be equal to the electric field multiplied by the radius squared divided by the constant k. Again, k is just 1 over 4 pi epsilon naught. The electric field is going to be 1150 newtons per coulomb. The radius is going to be half the diameter, so 0.16 meters. Make sure you remember to square that guy. And then 9 times 10 to the 9th. And I'm going to need 3.275 times 10 to the negative 9th coulombs of charge on this guy. Now, to get the number of electrons, I can simply divide the charge that I need divided by the charge of an electron. That's going to give me the number of electrons. So that's going to be 3.275 times 10 to the negative 9th coulombs divided by the charge of one electron, which is going to be 1.602 times 10 to the negative 19th coulombs. And that's going to give me 2.04 times 10 to the 10th electrons. And lastly, 2223. Here we have a sphere with a radius of r, and it tells us that r is going to be 0.355 meters. It tells us we know what the electric field is at a distance of 0.145 meters from the surface of the sphere, so we have to be careful here. We know what the electric field is right there. So let's go ahead, and what we're trying to solve for is we're trying to solve for the charge density, being the charge inside divided by the volume of the sphere. So first let's go ahead and solve for the charge. If I go ahead and I draw my Gaussian surface to be a sphere, we can write Gauss's law. The integral of E dotted with dA is going to be equal to the charge enclosed divided by permeability of free space. I've drawn a sphere, so I can simply write E multiplied by the area of the sphere, 4 pi radius squared. That's going to be equal to the charge enclosed divided by epsilon naught. I'm trying to solve for the charge enclosed, so I'll go ahead and move epsilon naught right there. And I can say, well, I know what the electric field is. That's going to be 1750. Epsilon naught, 8.85 times 10 to the negative 12th. Multiply that guy by 4 pi. Be very careful here with r. It's not going to be 0.145. It's going to be 0.145 plus 0.355. So that's going to be 0.5. And I square that guy. And I'm going to come up with the charge that is enclosed to be 4.866 times 10 to the negative 8th coulombs. I'm looking for my charge density, so that's going to be the charge enclosed divided by the volume of the sphere, so 4/3 pi big radius cubed, so 4.866 times 10 to the negative 8th divided by 4/3 pi. The radius of the sphere is 0.355. Don't forget to cube that guy. And we're going to get a charge density of 2.6 times 10 to the negative 7th coulombs per cubic meter. Volume is cubic meter, charge is coulombs. For part B, what we could do is we could draw a Gaussian surface inside the sphere at a distance of 0.2 meters. Or we can recall from example 22.22, I came up with the electric field inside an insulating sphere to essentially be K multiplied by Q multiplied by R divided by the radius of the larger sphere cubed, where K is just 1 over 4 pi epsilon naught. So that's going to be 9 times 10 to the 9th. Q is the charge I found above, 4.86 times 10 to the negative 8th. The radius of the sphere that I'm adding in there is going to be 0.2. That would be my Gaussian surface. And then the radius of the big sphere, 0.355. Make sure you cube that guy. And we're going to come up with an electric field at 0.2 meters be equal to 1957.7 with the value of with the unit of Newton per Coulomb.